According to National Electrical Code Table 220.12, an elderly housing community centre falls under the occupancy classification of residential board and care occupancy. You can use the optional method for multi-family dwelling calculations. This method allows you to calculate the dwelling unit load separately from the non-dwelling area load. The non-dwelling area includes the library, common corridor, piano room, mechanical and electrical rooms, offices, and fitness room. The non-dwelling area's square footage is 19,066 square feet. According to National Electrical Code Table 220.43, the volt-amperes per square foot for non-dwelling areas is 3.5 volt-amperes per square foot. Therefore, the non-dwelling load is 19,066 square feet times 3.5 volt-amperes per square foot, which equals 66,731 volt-amperes. There are a total of 32 dwelling units. According to National Electrical Code Table 220.43, the volt-amperes per square foot for residential dwelling units is 13.5 volt-amperes per square foot. The total dwelling unit square footage is 57,198 square feet. Therefore, the dwelling unit load is 57,198 square feet times 13.5 volt-amperes per square foot, which equals 770,673 volt-amperes. The total load for the elderly housing community centre is the sum of the non-dwelling load and the dwelling unit load. Total load equals 66,731 volt-amperes plus 770,673 volt-amperes, which equals 837,404 volt-amperes. Therefore, the service size for the elderly housing community centre should be 837,404 volt-amperes. When calculating electrical loads, you must consider several factors to ensure safety, efficiency, and compliance with the National Electrical Code. Firstly, understanding occupancy classifications is crucial. The National Electrical Code categorizes buildings based on their usage, and these classifications determine the minimum lighting load requirement. These requirements are specified in volt-amperes per square foot. For example, dwelling units have different load requirements than office buildings or storage facilities. Secondly, calculating the general lighting load involves multiplying the square footage of the area by the volt-amperes per square foot requirement specified for that occupancy. This calculation provides the baseline load for lighting. However, it is essential to include additional loads for receptacle outlets and any specific equipment that will be used in the space. Thirdly, receptacle outlets are typically calculated based on the number of outlets in a given area. The National Electrical Code specifies a minimum volt-ampere value for each receptacle outlet, which must be included in the overall load calculation. This ensures that the electrical system can handle the demand from devices plugged into these outlets. Furthermore, any specific equipment, such as HVAC systems, motors, or specialized machinery, must be accounted for separately. The nameplate rating of the equipment provides the volt-ampere or wattage information needed to include these loads in the calculation. In addition to the general lighting load, receptacle outlets, and specific equipment, you must consider demand factors. Demand factors are percentages that can be applied to reduce the calculated load based on the likelihood that all connected loads will not be operating simultaneously. These factors vary depending on the type of occupancy and the number of circuits or appliances. The National Electrical Code provides tables that specify demand factors for various situations. After calculating the total connected load and applying any applicable demand factors, the next step is to determine the size of the service entrance conductors and overcurrent protection. The service entrance conductors must be sized to carry the calculated load continuously without overheating. The overcurrent protection, such as circuit breakers or fuses, must be sized to protect the conductors from overload and short circuits. The National Electrical Code provides guidelines and tables for conductor sizing based on the ampacity of the conductor and the applicable correction and earthing factors. Correction factors are applied to adjust the ampacity of the conductor based on the ambient temperature, while directing factors are applied when multiple conductors are bundled together in a conduit or cable. These factors ensure that the conductors can safely carry the intended load under various conditions. For overcurrent protection, the National Electrical Code specifies that the overcurrent device should be sized no higher than the ampacity of the conductor it is protecting. This prevents the conductors from being overloaded and potentially causing a fire. However, there are exceptions to this rule, such as when dealing with motor circuits or specific types of equipment. In these cases, the overcurrent device may be sized higher than the conductor ampacity to allow for the inrush current of the motor or equipment. It is crucial to consult the National Electrical Code for specific requirements and exceptions related to overcurrent protection. When performing electrical load calculations, it is essential to use the latest edition of the National Electrical Code and to consult with a qualified electrical engineer or electrician. The National Electrical Code is updated regularly to reflect changes in technology and safety standards. Failure to comply with the National Electrical Code can result in electrical hazards, property damage, and legal liabilities. In summary, calculating electrical loads involves several steps, including understanding occupancy classifications, calculating the general lighting load, accounting for receptacle outlets and specific equipment, applying demand factors, and determining the size of the service entrance conductors and overcurrent protection. By following the guidelines and tables provided in the National Electrical Code, you can ensure that the electrical system is safe, efficient, and compliant with applicable standards. Remember to always consult with a qualified professional for complex or critical electrical calculations. Additionally, when performing electrical load calculations, it is important to consider future expansion or changes in occupancy. Electrical systems are typically designed to accommodate future growth, so it is prudent to include additional capacity in the calculations. This can prevent the need for costly upgrades or modifications in the future. Furthermore, if there are plans to change the occupancy of the building or add new equipment, the electrical load calculation should be revised accordingly. This ensures that the electrical system can handle the new demands without being overloaded. Another important aspect of electrical load calculations is to consider energy efficiency. Energy-efficient lighting, appliances, and equipment can significantly reduce the overall electrical load and lower energy costs. When selecting lighting fixtures, consider using LED lamps, which consume less energy and have a longer lifespan than traditional incandescent or fluorescent lamps. Similarly, when selecting appliances, look for Energy Star-rated models, which meet strict energy efficiency guidelines. In addition to energy-efficient equipment, consider implementing energy management strategies, such as occupancy sensors and dimming controls. Occupancy sensors can automatically turn off lights in unoccupied areas, while dimming controls can adjust the lighting levels based on the amount of natural light available. These strategies can further reduce the electrical load and save energy. When calculating electrical loads for multi-family dwellings, the National Electrical Code provides specific guidelines for determining the demand factors for individual dwelling units. These demand factors take into account the diversity of loads in residential occupancies, when not all appliances and lighting are likely to be used simultaneously. The demand factors vary depending on the number of dwelling units and the size of the individual loads. In addition to the dwelling unit loads, you must consider the common area loads such as lighting, receptacles, and HVAC systems. These loads should be calculated separately and added to the total load for the building. For large commercial or industrial facilities, the electrical load calculations can be quite complex, involving numerous circuits, equipment, and demand factors. In these cases, it is highly recommended to use specialized software or consult with a qualified electrical engineer. These professionals have the expertise and tools to perform accurate and comprehensive load calculations. Electrical load calculations are not a one-time task. They should be reviewed and updated periodically to reflect changes in occupancy, equipment, and energy efficiency measures. Regular reviews can identify potential problems or inefficiencies and ensure that the electrical system continues to meet the needs of the building. In summary, electrical load calculations are a critical aspect of electrical design and safety. By understanding the principles and guidelines outlined in the National Electrical Code, you can ensure that the electrical system is properly sized, protected, and efficient. Remember to consider future expansion, energy efficiency, and the specific requirements for different types of occupancies. Always consult with a qualified professional for complex or critical electrical calculations. Furthermore, consider the impact of renewable energy sources on electrical load calculations. With the increasing adoption of solar panels and other renewable energy systems, it is important to integrate these sources into the overall electrical design. Solar panels can reduce the amount of electricity drawn from the grid, thereby lowering the overall electrical load. However, the electrical system must be designed to safely accommodate the integration of renewable energy sources. This includes proper sizing of inverters, disconnects, and overcurrent protection devices. The National Electrical Code provides specific guidelines for the installation and integration of renewable energy systems. In addition to solar panels, other renewable energy sources, such as wind turbines and fuel cells, may also impact electrical load calculations. Each type of renewable energy system has its own unique characteristics and requirements, which must be carefully considered during the design process. Another factor to consider in electrical load calculations is the impact of electric vehicle charging. As electric vehicles become more popular, the demand for charging stations is increasing. Electric vehicle charging stations can add a significant load to the electrical system, especially if multiple vehicles are charging simultaneously. When designing electrical systems for buildings with electric vehicle charging stations, it is important to accurately calculate the additional load and ensure that the system can handle the demand. The National Electrical Code provides guidelines for calculating the load for electric vehicle charging stations, including demand factors and conductor sizing requirements. In addition to the electrical load calculations, it is also important to consider the grounding and bonding requirements for electric vehicle charging stations. Proper grounding and bonding are essential for safety and to prevent electrical shock hazards. Furthermore, consider the impact of energy storage systems on electrical load calculations. Energy storage systems, such as batteries, can store excess energy generated by renewable energy sources or drawn from the grid during off-peak hours. This stored energy can then be used to supplement the electrical supply during peak hours, reducing the overall electrical load. When designing electrical systems with energy storage systems, it is important to consider the capacity of the batteries, the charging and discharging rates, and the control strategies. The National Electrical Code provides guidelines for the installation and integration of energy storage systems. Another important aspect of electrical load calculations is to consider the impact of harmonics. Harmonics are distortions in the electrical waveform that can be caused by nonlinear loads such as electronic devices, variable frequency drives, and LED lighting. Harmonics can cause a variety of problems, including overheating of transformers and conductors, malfunctioning of equipment, and increased energy losses. When designing electrical systems with significant nonlinear loads, it is important to analyze the harmonic content and implement mitigation strategies, such as harmonic filters or line reactors. The Institute of Electrical and Electronics Engineers provides standards and guidelines for harmonic analysis and mitigation. In addition to the technical aspects of electrical load calculations, it is also important to consider the economic factors. The cost of electricity can vary significantly depending on the time of day, the season, and the utility provider. By carefully managing the electrical load and implementing energy-efficient measures, it is possible to reduce energy costs and improve the overall profitability of the building. Energy management systems can provide real-time monitoring of electrical consumption and allow for adjustments to be made to optimize energy usage. In summary, electrical load calculations are a complex and multifaceted process that requires careful consideration of various factors, including occupancy classifications, equipment loads, demand factors, renewable energy sources, electric vehicle charging, energy storage systems, harmonics, and economic factors. By following the guidelines and standards provided by the National Electrical Code and other organizations, and by consulting with qualified professionals, you can ensure that the electrical system is safe, efficient, and reliable.